UDC.
Welcome, everybody, and thanks for being here. My name is Bill Kraft, and I'm UDC's Vice President of System Architecture. Over the next 20 to 25 minutes, I'll be talking about cloud technologies and how they can modernize your enterprise GIS deployments. Before we get into those topics, here's a little bit about UDC. We partner with our utility clients to provide high-value solutions through geospatial and other technologies and processes. Most of our business is with utilities that leverage Esri GIS. We're an Esri Platinum partner. On the right-hand side is a quick peek at the accreditations and awards we've won throughout the years. A bulk of what we do spans multiple types of GIS service offerings, but we have several software product solutions developed on core Esri technology as well. It's worth noting that the cloud technologies I'll cover today provide significant benefit for your enterprise GIS deployments in a variety of ways. These include reduced server maintenance, increased availability, enhanced security, refined automation, boosted flexibility, simplified deployment, and improved performance. My presentation today is primarily focused on deployment and configuration in terms of what's possible and what we've found from doing it ourselves. If you'd like to chat further about the benefits above, or about how to configure cloud services and resources, or about whether the cloud is even right for you at all, feel free to reach out to me. My contact information will be listed on the final slide. An enterprise GIS involves so many components, and these components translate very nicely to cloud-native technologies. We won't be able to cover every component, so we'll do a deep dive today on these 6 specifically. Our deep dive will focus on leveraging cloud-native technologies. You'll see that today's presentation centers around 2 major cloud providers, AWS and Azure, but there are others out there that may be right for you. So our deep dive begins with the database component of an enterprise system, specifically for enterprise geodatabases. The ArcGIS platform supports several different databases hosted in the cloud. We took a closer look at Aurora Postgres Compatible Edition from AWS Relational Database Services, or RDS. It's a great serverless option that offers auto-scaling and multi-zone deployments with standby replicas. Additionally, AWS can automatically perform minor version upgrades during your configured maintenance windows. You have control over the underlying storage disk type, as well as several database security mechanisms based on your needs. Esri also provides a nice set of deployment automation tools, such as Cloud Formation templates and Cloud Builder, to help you stand up an enterprise geodatabase in AWS. With Aurora databases, AWS offers quite a few value-add options, such as Elastic Cache Cluster add-on for improving read performance, an RDS proxy add-on for pooling and sharing connections to get better scaling, several other capabilities as well, like write forwarding, blue-green deployments, performance insights, and enhanced monitoring logs. We created an Aurora database cluster, set up an enterprise geodatabase, walked through configuring some of the settings we talked about previously, and tested a few of those options out. After loading some sample gas and electric utility data, we built out a secondary cluster in a different region and added a reader replica to publish services against. By the way, the services we published were in the same region as the reader replica. Keeping your data and services in the same region is best practice deployment pattern. No significant performance issues were found when rendering or editing the REST services. We also found that orchestrating switchovers and failovers between the 2 clusters was straightforward and reliable through the AWS console. The second enterprise system component we dug into is network file shares, specifically around ArcGIS Enterprise configuration and content. For this component, we explored Azure's storage account file share technology. Especially with multi-machine deployments of ArcGIS Server or Portal for ArcGIS, Azure's file share solution is a great way to go because it provides options for redundancy, disk type, encryption, and security in general. Further, it provides an SMB share that offers read consistency, low latency, and very little file concurrency, all of which are critical to the ArcGIS Server configuration store and directories, as well as the portal for ArcGIS content directory. As a quick note, you should always back up the config store regularly to avoid or reduce potential corruption issues and to increase the likelihood of a successful restore. This is the case with any network file share solution. Azure also gives you several additional options when configuring a file share, such as soft deletes, large file shares up to 100 terabytes, threat detection, snapshots, and several others. We created an ArcGIS Enterprise-based deployment within Azure and moved the ArcGIS Server config store and directories, as well as the portal content folder and logs, to file shares under an Azure store account. Doing this allowed for the file shares to be concurrently accessible by multiple nodes. After creating a file share private network endpoint to allow that SMB access from the base deployment virtual machines, we configured daily backups to an Azure Vault and set up a retention period. During our configuration and testing, we found Azure file shares to be highly available and flexible for DR purposes because they span multiple zones and replicate nicely to other regions. The third enterprise system component we'll cover today is web applications, specifically around the ArcGIS Web Adaptor. We look closer at both Azure and AWS cloud platforms in terms of the Web Adaptor. Azure's Web App Service and AWS's Elastic Beanstalk are excellent fits for Web Adaptor deployments. My favorite personally is putting the Web Adaptor in Azure, specifically for the Azure Web App Services, mainly because of how easy deployment is and because it is mostly serverless. Both support the .NET and Java versions of the Web Adaptor, and they provide auto scaling and redundancy, and both offer managed platform updates and patches. There are several deployment options available, but it can be as easy as uploading a custom zip package. You can also parameterize the URL, the ID, and the shared key properties in the Web Adaptor JSON configuration file through deployment pipelines within AWS or Azure to make things even easier. We stepped through the Web Adaptor deployment and configuration process on AWS and Azure. The process initially requires a server to install the Web Adaptor, in our case, the .NET Web Adaptor for IIS on Windows, and subsequently zip the directory. Configuration can occur beforehand, manually in a text file editor, or it can occur after deployment. After Web Adaptor deployment and configuration was completed, we set up security to include enabling HTTPS, binding SSL certificates, and configuring CORS restrictions. Furthermore, we configured our Azure Web Adaptor, Web App Service, and AWS Elastic Beanstalk applications to autoscale based on demand. The autoscaling capabilities of both platforms lend themselves well to an ever-changing number of concurrent users. We found that Azure's deployment slot and AWS's rolling update functionalities greatly simplified change management in terms of upgrades or reconfigurations because it reduces downtime significantly. Finally, these serverless approaches greatly reduce or eliminate, in some cases, server maintenance and overall footprint. The fourth, fifth, and sixth enterprise system components we looked at were combined due to their close relationship with one another. These components are the batch jobs, the scheduled processes, and the automated tasks of an enterprise system. For an enterprise GIS, this can mean a lot of different things. It could include data extracts and exports to support integrations, or it could involve tools that augment attribute data population during editing workflows. Our focus for these components was on AWS cloud native technologies, primarily involving Lambda functions with support from S3 buckets, Event Bridge, and a database trigger within the Aurora database. Lambda functions provide repeatable processes which can be executed with a web request, and they support input variables that get passed to Node.js, Python, and other natively supported codebases. Other AWS services can invoke Lambda functions as well, making them very flexible across the AWS cloud landscape. They're designed for short-term scripts or applications, and therefore are limited to 15-minute durations. So we created 2 Lambda functions based on custom Python scripts. Let's talk briefly about the first Lambda function, which performs a batch export of GIS attribute data into text files for downstream import into another system. If you recall from earlier, we had set up Aurora Enterprise Geodatabase with sample gas and electric utility GIS data. Then we had published some feature service against a read-only replica of that data. We then configured Event Bridge to run the batch export Lambda function on a 12-hour schedule. The Python script behind the Lambda function made REST queries to the published feature services to generate the text files of the attributes in JSON and CSV formats, and then drop those files into an S3 bucket. One key ingredient to get this working was to create a VPC endpoint for the S3 bucket and secure it using AWS identity and access management policies. The other Lambda function auto-populates an attribute field during an edit session, thus simulating an API call from an integrated asset management system, for example. To facilitate this workflow, we created a custom row-level trigger in the database and an accompanying function within Aurora for the sample gas pipeline data. The trigger and function were designed to populate the installation date field of a pipeline asset once the GIS editor fills in the unique asset attribute value. This works nicely with unversioned or branch version data because only one table is in play compared to traditional versioning, which joins the base table to delta tables. After saving edits, any assets where the asset ID got populated automatically retrieved their installation date attribute value from an integrated asset management system through a direct REST API call, in our case, to the Lambda function to simulate that third-party system. We found no significant performance issues testing this configuration, especially with a small number of edits. All records received their installation date values in well under the 3-second timeout we configured for the Lambda function. I wanted to mention that the reason for not using an attribute rule is because those do not allow an HTTP call. Additionally, a lot of the AWS resources are Lambda function aware, so calling Lambda functions is natively supported very nicely across many other AWS resources. I would be remiss if I did not caution you to be cognizant of performance impacts when using triggers and to be mindful of corruption issues within the database if they're not implemented correctly. As a side note, adding custom Python modules to Lambda functions is supported, such as ArcPy and the ArcGIS API for Python modules, and those can be loaded into a Lambda function environment very quickly. In summary, we created batch jobs through Lambda functions and set them up as scheduled processes using Event Bridge. We also achieved task automation through Lambda functions and the supporting Aurora database trigger when editing within ArcGIS Pro. In my final message, I want to illustrate the breadth of how enterprise GIS components can translate to a cloud-native technologies. I also want to highlight the fact that these cloud resources are all privately secured through AWS Virtual Private Cloud, or VPC, and Azure's Virtual Network VNet technologies. These are just a few of the ways in which your enterprise GIS can leverage a cloud platform and embrace more modern deployment patterns. Thank you for spending the time to hear about UDC and what we're doing lately with cloud technologies. Reach out to me if you would like to chat further or have questions.
UDC